this is the first video of a first vector series for OCR AS Core Pure Further Mathematics. It will revise vector topics covered at GCSE and at AS Maths, including notation. At GCSE, you will have been introduced to vectors in 2 dimensions. So a vector may be written as AB with an arrow above it, or as A underlined. You should already be aware that vectors have both magnitude and direction, and they can be used as position vectors. A vector on a 2-dimensional grid can be given in component form. So, vector A equals element A1 in the x direction and A2 in the y direction. In printed text, you may see vectors in bold, but we will use the notation of vectors being underlined, i.e. not in bold. Vectors may be added, subtracted, and multiplied by a scalar. Let's look at some examples where we have that vector A equals 4 minus 1, and vector B equals 1, 2. So, here we have A, which is 4 minus 1, if we take this to be the origin. And B would be 1, 2, would be that red line there. If we're looking at A plus B, just to remind you how we add vectors, we would have 4 plus 1 is 5, and minus 1 plus 2 is plus 1. Showing this on the diagram, that would give us A and then B up to this point here. So that would be A plus B, shown that line there. If we were to do A minus B, we would have 4 minus 1 minus 1, 2. So 4 minus 1 is 3, and minus 1 minus 2 is minus 3. In which case, A, and then you can see that this is minus B in terms of it's in the opposite direction to B. And therefore that point 3 minus 3 is A minus B. 2B is just multiplying B by the scalar 2, or the constant number 2. And that would give us 2 1s are 2, 2 2s are 4. And that's like repeating B and then B again. So that point up there would represent the 2B. The modulus or magnitude or size of a vector may be written using this notation. So either modulus of AB with the arrow over it, or modulus of A underlined. This may be calculated using Pythagoras' theorem. So, where A consists of the elements A1 and A2, it will be the square root of A1 squared plus A2 squared. Note, therefore, that this will always be positive. I expect you are used to working with the x and y axes in 2 dimensions. However, because we're going to be moving on to 3 dimensions, let us introduce the idea that in 2 dimensions we can write vectors in terms of unit vectors, I and j, which you can see by this diagram are perpendicular. Thus the vector notation becomes A, or vector A, equals elements A1, A2, is A1 in the I direction and A2 in the j direction. A unit vector in a particular direction is called A hat, and this is equal to the vector A divided by the magnitude of A. Let's look at an example. If A equals 4 minus 1, then the magnitude of A will be equal to the square root of 4 squared plus 1 squared, or in other words, the square root of 17. And a hat as a vector would be 1 over square root 17 of 4 minus 1. And it's quite normal to write the fraction outside of the brackets. You will have come across vectors being used to give position vectors of a point before. The position vector of a point is a vector going from the origin to the point. In this diagram here, OP is the vector P, is minus 4, 3. And OQ, or the vector Q, is 3, 2. If we wanted to find PQ, we would do that by looking at Q minus P, which would give us 7 minus 1. And if we were to draw that on this diagram, that would be that vector there. Parallel vectors have the same direction. So in other words, vectors will be multiples of each other, just as we looked at with the b and then 2b in an earlier slide. So if we were to ask which of these are parallel vectors, we're looking to see which of them are multiples of the other. Considering 8 minus 4, we can see that that's minus 2 of minus 4, 2, and is also equal to minus 4 of the minus 2, 1. So those three vectors are parallel vectors. However, 2 minus 4 is not parallel. You may wish to pause the video here and draw those vectors on graph paper just to check. Moving on then from 2 dimensions to 3 dimensions, and this bit will be new for you. The axes used for 3D are I, J and K. If you can try and visualize this in 3 dimensions, you can see that the I unit vector should be seen as coming out of the page, and that I, J and K are still perpendicular. Thus the vector notation for a vector A in 3D will be given by the elements A1, A2, A3, equal to A1 in the I direction, A2 in the J direction, plus A3 in the K direction. Remembering that I, J and K are all unit vectors. 3D vectors may be added, subtracted and multiplied by a scalar exactly the same way as for 2D vectors. In addition, the magnitude of a 3D vector is also found by using Pythagoras' theorem, but in this case it's the square root of a1 squared plus a2 squared plus a3 squared. Let's have a look at these examples here. If vector A is 2i plus 4j plus 3k, then the magnitude of A will simply be the square root of 2 squared plus 4 squared plus 3 squared, or square root of 29. And the magnitude of B, where B is minus 4i plus 2j plus k, will be the square root of 4 squared plus 2 squared plus 1 squared, or the square root of 21. Strictly speaking, this would have been minus 4 squared, which is obviously the same value of 16. You may wish to look at GeoGebra and play around with the idea of 3D vectors, changing the values of the elements in the directions I, J and K. In the next session, we will look at multiplying vectors to form a scalar product.